problem we want to solve this week is as follows. We're given a sequence of numbers, a sub 1, a sub 2, a sub 3, and so on, which are defined as follows. The first two numbers in the sequence are equal to 103. And then each term after that is defined as the difference of the two terms that came before. So a sub n plus 1 equals a sub n minus a sub n minus 1 for every n greater or equal to 2. So this fancy upside down capital A is read as follows. You say, for every n greater than or equal to 2. This could also be written as for values of n equal to 3, 4, 5, and so on. So our sequence is defined recursively in this way, and we're being asked to calculate the sum of the first 2006 terms in the sequence. To solve the problem, I'm going to make a table to figure out the first few terms in the sequence, like this. So the relation is given as a sub n plus 1 is equal to a sub n minus the previous term, a sub n minus 1, for n equal to 3, 4, and so on. And it has two initial conditions. So when n is 0, a sub n plus 1 will be a sub 1, a sub 0 plus 1 is a sub 1, which is given to us as a value of 1003, and likewise when n is 1, a sub n plus 1 will be a sub 2, which is given to us as 1003 as well. And these are our initial conditions. So a sub 1 and a sub 2 are the initial conditions of the sequence. And then the terms that follow after that, so when n is 2, a sub n plus 1 is a sub 3, and it's equal to a sub n. So for n equaling 2, that will be a sub 2 minus a sub n minus 1. So for n equaling 2, that's a sub 2 minus 1, which is a sub 1. And a sub 2 is 1003, and a sub 1 is 1003. So that's 1003 minus 1003, which is 0. So what we have so far is a sub 1 and a sub 2 are 1003, that's given, and a sub 3 is 0. And can we work out a sub 4, the next term? So when n is 3, a sub n plus 1 will be a sub 4, and the recurrence relation says that that's going to be a sub n, which is a sub 3, minus a sub n minus 1, which is a sub 2. And so I'm going to take a sub 3 minus a sub 2, which is 0 minus 1003, so 0 minus 1003, and so a sub 4 is negative 1003. And then, continuing on in this way, let's see if there's a pattern. Continuing in this way, when n is 4, we get a sub 5, which is equal to a sub 4 minus a sub 3, which is equal to negative 1003 minus 0. So we're getting negative 1003 again. And then a sub 6 is equal to a sub 5 minus a sub 4, which is equal to negative 1003 minus negative 1003, which is 0. And what's the next term? When n is 6, we're getting a sub 7 is a sub 6 minus a sub 5, which is 0. Take away negative 1003, which is 1003. And let's do one more term in the sequence. When n is 7, a sub n plus 1 is a sub 8, which is equal to a sub 7 minus a sub 6, which is 1003 minus 0, which is 1003. So we can see we have cycled back around to the beginning of the sequence. This is where we started. So the sequence we have is going like this. It starts with 1003 twice, then we get a 0, then we get negative 1003 twice, then we get a 0, and then we cycle back around to where we were at the top with the value of 1003 twice. And I don't have to compute any more values because the pattern is the same, and we're just going to keep going around and around in a cycle like this, repeating these same 6 numbers. 1003 twice, 0, negative 1003 twice, and then 0. So we have a 6th cycle. So I don't need to compute the next terms to know that a sub 8 will be following this pattern. 1003, 1003, 0, negative 1003, negative 1003, 0, and so on, forever and ever and ever. And these 6 numbers, notice, add up to 0. And no matter where I start in the sequence, I'm cycling through those same 6 numbers. So for example, if I start with a sub 7 and I want to proceed a sub 8, a sub 9, a sub 10, and so on, I'm going to cycle through these same 6 numbers, starting with 1003. So 1, 2, 3, 4, 5, 6. And I cycle through the same 6 numbers every time, and those 6 numbers add up to 0. So now that we understand how this sequence works, we're ready to answer the question, which was to calculate the sum of the first 2006 terms. So as we're cycling through this sequence, most of these terms are adding up to 0. So if we divide 2006 by 6, we get 334 with a remainder of 2. So 2006 is equal to 2 plus 334 times 6. So we could add up the first two terms of the sequence, and then the remaining 334 times 6 terms are going to add up to 0, like this. So we have A1 plus A2 plus A3 plus A4 plus, and so on, all the way up to A sub 2006, and from 3 until 2006, we have 334 times 6. So we have 334 groups of 6 consecutive numbers, each adding up to 0. So my total sum is equal to A sub 1 plus A sub 2 plus 334 times 0. So 0 for each one of those 334 groups of consecutive numbers that add up to 0. So this is A sub 1 plus A sub 2, which is 2006. And I think we are rewarded with an answer which is the same as the date in which this question was written. Now that you're getting the hang of this, how about we try one more problem like this for practice? So for the next problem, let's calculate the sum of the first 1,723 terms of this sequence. A sub n plus 1 is the square root of 2 times the previous term, a sub n, minus the term that came before that, a sub n minus 1, for n equals 2, 3, 4, and so on, where our initial conditions are a sub 1 is 2 and a sub 2 is 5. So I can solve this problem in the same way as I did before by making a table of the first few terms in the sequence like this. So I'm writing down the formula for a sub n plus 1. Again, that's the square root of 2 times a sub n minus a sub n minus 1. And the initial conditions, when n is 0, we get a sub 1, which is given to be 2. And when n is 1, we get a sub 2, which is given to be 5. Next, when n is 2, we have a sub n plus 1 is a sub 3, which is the square root of 2 times a sub n, so that's going to be a sub 2 minus a sub n minus 1, which is a sub 1. We have a little bit of algebra to do there. That's going to be square root of 2 of this number minus this number. So that's 5 root 2 minus 2. So I'm getting 5 root 2 minus 2. And the next number, let's see how that goes. When n is 3, I'm getting a sub 4 is equal to the square root of 2 times a sub 3 minus a sub 2. So I have to take the square root of 2 of this number minus the number that came before that. So let me get a piece of scrap paper and I'll work that out. And so a sub 4 is the square root of 2 times a sub 3, but that's 5 root 2 minus 2. Oops, sorry. And so again, a sub 4 is the root 2 times the previous number minus the number that came before that. So I've written down root 2 of the previous number and then minus the number 5, which came before that. And this works out to be, that's 5 times 2 minus 2 root 2 minus 5. With the distributive law, when I multiply the root 2 through into this difference, that's 5 times 2 minus 2 root 2. And so finally, I'm getting 2 5s minus 1 5, which is just 1 5, minus 2 root 2. So a sub 4 is 5 minus 2 root 2. And let's do one more term. So how about a sub 5? Let me move this out of the way. So when n is 4, we're getting a sub 5, which is the root 2 of the previous number, a sub 4, minus the number that came before that, a sub 3. And I'll show the math one more time. So this time I'm getting, I need a piece of scrap paper again. So a sub 5, okay, so that's the root of 2 times the number that came before, which is 5 minus 2 root 2, and then minus the number that came before that, which is 5 root 2 minus 2. Careful, watch the parentheses here because I have to subtract this entire difference to get the right answer. And so using my distributive law, the square root of 2 times this difference is 5 root 2, and then minus 2 times root 2 times root 2, which is 2 times 2, which is 4, minus 5 root 2, and then plus 2. So the 5 root 2's cancel because 5 root 2 minus 5 root 2 is 0, and I'm getting a sub 5 is minus 4 plus 2, which is minus 2. So a sub 5 is equal to minus 2. And we just continue the arithmetic in that same fashion, and I'll give you the answers. They look like this. So when n is 5, I got a sub 6, which is square root 2 a sub 5 minus a sub 4. And for that result, I got minus 5. And then for a sub 7, I got negative 5 root 2 plus 2. So I'm starting to see a pattern. I'm not quite cycling back around yet, but I started with 2 and 5, and now I'm getting negative 2 and negative 5. And the next number was 5 root 2 minus 2, and I'm getting a negative of that, negative 5 root 2 plus 2. And that's what happens, actually. So calculate it out and check my results, but you should find for a sub 8, the next number will be the negative of this one, which is negative 5 plus 2 root 2. And then I found a sub 9 is equal to 2, and a sub 10 is equal to 5. And I'm finally back to where I started with my initial conditions of 2 and 5. So for this problem, I can see that this time I'm getting an 8 cycle. because the numbers a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, a sub 7, and a sub 8 form an 8 cycle, where my 8 cycle starts out with the 4 positive numbers 2, 5, 5 root 2 minus 2, and 5 minus 2 root 2, and then goes through the negatives of those 4 numbers, negative 2, negative 5, negative 5 root 2, plus 2, and negative 5 plus 2 root 2. And I'm back to where I started with the initial conditions of 2 and 5. And I keep going around and around, repeating these same 8 numbers over and over and over again as I continue down the sequence. So no matter where I start in the sequence, as I proceed down the sequence, I'm cycling through the same 8 numbers. For example, if I were to start with a sub 5 and keep going a sub 6, 7, 8, 9, 10, 11, 12, 13, and so on down the sequence, then we would cycle through the numbers starting at minus 2, and we would get these 4 negative numbers, 1, 2, 3, 4. Then we would come back around up to these 4 positive numbers, 1, 2, 3, 4. Like that. So I'm cycling through 1, 2, 3, 4, 5, 6, 7, 8 numbers. The same 8 numbers every time. And those 8 numbers add up to 0 because it consists of the 4 positive numbers and the negatives. And so whenever I go through 8 consecutive numbers in the sequence, those 8 consecutive numbers will add up to 0. Same way as in the problem of the week. Only in the problem of the week it was a 6 cycle. And so, in order to answer the question, what is the sum of the first 1,723 terms, I have to figure out how many groups of 8 I've got and what's my remainder, and then I'll know my answer. So I'm going to divide 1,723 by 8. So let's see what I'm getting. When I divide 8 into 1,723, check my work and see if you agree with me. I got 215 with a remainder of 3. So that means that the 1,723 terms is equal to 3 plus 215 groups of 8 consecutive numbers that add up to 0. So the sum of the first 1,723 terms goes like this: a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5 plus a sub 6 plus, and so on, all the way up to a sub 1,723. But these last terms give me a list of 215 times 8 terms. So that gives me 215 groups of 8 consecutive terms, each one adding up to 0. So this whole sum is just 0, like before. And so my answer is a sub 1 plus a sub 2 plus a sub 3 plus 215 times 0, or just the sum of the first 3 terms, which is 2 plus 5 plus 5 root 2 minus 2. And so that's just 5 plus 5 root 2. And so my answer is 5 plus 5 root 2. Check my arithmetic and see if you agree with me. If you'd like to try some more, I've cooked up a few more similar practice problems for you to try. Here are some practice problems for you to try, which are similar to the problem of the week. I'll give you the answers at the end of the video. The kinds of sequences we've looked at in this video are generated by an equation of this form, where a sub n plus 1 is equal to some constant times a sub n plus another constant times a sub n minus 1. If you'd like to learn more about these kinds of equations, there's a name for this. This is called a linear homogeneous recurrence relation of degree 2 with constant coefficients. The reason it's called linear is because when the equation is rearranged with all of its terms on the left-hand side of the equation, we get a linear combination of the terms in the sequence. We didn't complicate the equation with nonlinear terms. For example, we didn't square the terms in the sequence, like this. If we did that, this kind of equation would be harder to solve. This equation is called homogeneous because of the 0 on the right-hand side here. If we added a non-sequence term to the equation like this, then we would get a non-homogeneous equation. A non-homogeneous equation is generally harder to solve than a homogeneous one. The reason the equation is of degree 2 is because each term in the sequence depends upon the 2 previous terms that came before it. If each term depended on the 3 terms that came before it, then the equation would be of degree 3, and so on. And finally, the coefficients C1 and C2 in this equation are constants. They didn't have variable values, like, for example, n, or n squared, or cosine of n. These kinds of equations are well understood, and the examples that we've seen here only touch on the kinds of behavior exhibited by the sequences that result from the recurrence relation. Just for fun, here are a couple of famous examples of sequences which result from this special kind of recurrence relation. So if we set C1 and C2 equal to 1 in this recurrence relation, we get the Fibonacci sequence. And if we set C1 equal to 2 and C2 equal to 1, we get a sequence of numbers which are called the Pell numbers. I generated the first few terms of the Fibonacci sequence on my computer right here. So as you may know, each term in the sequence comes from adding the 2 previous terms that came before. So 2 is 1 and 1, 3 is 1 and 2, 5 is 2 and 3, and so on. A very well-known sequence. As you can see, calculating the sum of the first few thousand terms would result in a very large number indeed. And there is a formula to calculate that answer. Perhaps more interesting than the sum would be to take the ratio of 2 consecutive terms, which you can see I've made my computer do that here For example, the two consecutive terms 5 and 8. 8 divided by 5 is the same as 16 divided by 10, which is 1.6. Right here. As we progress down the Fibonacci sequence, these ratios get closer and closer to the golden ratio of 1 plus the square root of 5 over 2. I did a similar thing for the Pell numbers, like this. This time, each term is equal to twice the previous term plus 1 of the term that came before that. So for example, to get 12, we take twice 5 plus 2, which is 10 plus 2, which is 12. And to get 29, we take twice 12 plus 5, which is 24 plus 5, which is 29. And so on. This time, when we take the ratio of consecutive terms, the result is a sequence of ratios that converges to the silver ratio of 1 plus the square root of 2. As you can see, linear recurrence relations are interesting to study, and they exhibit interesting properties. Let's go back to the practice problems which I gave you, which are similar to the problem of the week. Watch out, this last one is a little bit tricky. It just requires a little more thought. You can pause the video here and give these a try. Press play when you're ready for the answers. Here are the answers to the practice problems. I hope you enjoy. Good luck.